Assalamu alaikum wa rahmatullahi wa barakatuh. In this video we will discuss this 30 watt SMPS circuit. It is PSAA30R-120-R. When we check datasheet for this series, it is 30 watt power supply and 12 volt. This 30 watt design, it comes in different setups: 12 volt 2.5 ampere, 15 volt 2 ampere, 24 volt 1.25 ampere, or 56 volt 0.54 ampere. So basically one of my viewer, he sent me these 10 pieces. This design, and as mentioned on the board, 30R120. So this number is 12 volt. And he contacted me that he purchased these power supplies and these are providing 57 volt. So let's check, and he wants some solution to make it 12 volt. We will also make it. This power supply does not have any circuit diagram available on the internet or any service manual from the manufacturer. I draw this circuit diagram. I will share this diagram. First of all, we will see its output. So its output DC voltage, so its output is 57 volt. It is 30 watt. Definitely its current rating is now 0.54 ampere. All these power supplies are working, functional, but the problem, every power supply is giving 57 volt. Friends, if you have not a good practical experience in power electronics, never try to repair, never try to test anything, because dangerous voltage are present in this power supply. Because 220 volt line voltage are present, 250 volt I am applying at the input. Then there is a fuse. Then we have 2.5 ampere 250 volt fuse. After that we have a capacitor. This capacitor is connected between line and neutral. Line and neutral points are here. So this line will go to fuse. After fuse, this line is reaching here. And here we have R1 and R1A 2.2 mega, which is connected. This end is connected to neutral. So this capacitor is connected between line and neutral. Then we have inductor here. It is dual line filter for EMI and RFI noises. High frequency spikes, high voltage spikes will be removed through this filter. This line passing through this filter reaching here. This line passing through filter reaching here. Here we have bridge rectifier. In the diagram, capacitor, 2 resistors, inductor. Sometime our fuse burns out again and again. So the first cause, so most of the time maybe this capacitor, if it is short circuit, it will pass the electrical current from this point, from this way. So it will damage this fuse. Or maybe we have voltage arrestor here, any MOV or anything. Short circuit in the parallel line can damage the fuse. Then we have inductor, dual line filter. After that we have a bridge rectifier. Then we have main bulk capacitor, DC capacitor, 68 microfarad, 400 volt for filtration to remove the ripples. This bridge rectifier will rectify the voltage and we will receive rectified voltage at this capacitor. DC voltage, I am receiving 349 volts DC, because this power supply will work from 90 volt to 264 volts. This time I am receiving 250 multiplied by 1.414, it is 353 volts. DC voltage at DC capacitor, it is 348 volt, some load and some ripples, so around 353 volts it must be available here. If I cannot find this voltage, that means this capacitor might be damaged. If I applied 250 volt AC, I multiply with this one, but at capacitor I receive around 250 volts. That means this capacitor is not holding charge. In that case, this capacitor is internally open, so it cannot hold the charge. In that case, we have to replace the capacitor. If our line voltage are 115 volt, multiply 1.414, in that case 162 volts should be available at the capacitor because it is a universal power supply. From positive line we have a jumper here that looks in black color. So this jumper is connected. This is positive side of the capacitor. So positive voltage are reaching here. Here we have two resistors, one capacitor C12, and we have here resistor inside parallel to this capacitor, and we have a diode here connected between these two lines. This resistor C, capacitor and diode, RCD Snubber Circuit is here. So it is connected across the positive line and transformer winding. Which one winding? Primary winding. Positive voltage are reaching directly to this winding, one end. Second end is connected to MOSFET, drain. This one is source. Source is connected with one resistor, 1 ohm resistor, jumper resistor, that is current sensor resistor, from this point to capacitor. Negative line, one resistor is here between this line and this line. It is reaching to the source. Here we have source. This one is drain. Drain is connected to transformer primary winding, one end. This resistor, 1 ohm resistor, will measure the current, how much current will flow from this 4N60 MOSFET. And the second end of the primary is connected to this RCD snubber and this point, and it is connected to positive side of the capacitor. 2.2 mega ohm, 2.2 mega ohm resistor, which is connected to positive DC rail, and it is connected to IC pin number 5. The same point, this positive DC rail is reaching here, and here we have 2 to 5, 2 to 5. This 2 to 5 code, that means 2, 2 and 5 zeros. It is 2.2 mega from this point to this end, and it is connected in series. Then it is connected to this point. It is connected here, and it is reaching from underside of this IC. This trace is from underside of this capacitor and this IC, and it is reaching at pin number 5. So this SMPS controller is 6-pin IC. Pin 1, 2, 3, 4, 5 and 6. I received comment from one of my viewer how we can find the pin number of any SMPS. What is the function of every pin? So let's trace it here. This dot. So this dot means here is pin number 1. Pin number 1 is connected here. It is connected here. So pin number 1, that is ground. Pin number 2, that is connected here, and it is reaching to this optocoupler. So the pin connected to this optocoupler, it is feedback pin. So pin number 1 is connected to ground. Pin number 2 is connected to this optocoupler, so it is feedback pin. Pin number 3 is connected to this resistor. So this resistor second end is connected to ground. So this is frequency resistor, frequency RT, that is called frequency setting resistor, timing resistor. Pin number 4, this point from underside this capacitor, this resistor. So pin number 4 is reaching here, and it is connected to R4, and R4 is connected to this point. So our this point, it is, this end is ground, this end is ground. We have 1 ohm resistor here inside. Here we have 1 ohm resistor, that is current sense resistor, for current measurement. 1.1 ohm resistor. 0.11 is multimeter error, 0.11 ohm. It is 1.11, that means 1 ohm resistor is connected to this point. How much current will flow from this point, and it will cause to drop voltage at this resistor. So this dropped voltage will reach from this resistor to this current feedback pin here. MOSFET, this end is connected to transformer primary winding. These resistors are connected here at this point, and we have one capacitor here to prevent this circuit from false switching, and it will monitor the current, how much current will flow from this primary ground. This is primary ground. One end of this main capacitor, bulk capacitor, is connected to primary ground. This ground is applied here. So current will flow from this line to this MOSFET to the positive of the capacitor. Pulses will provided from this IC. It will switch and it will cause to flow the current. At every pulse, how much current will flow? The product of I into R. 1 ohm resistor, and how much current will flow from this point? From this point, it will measure the dropped voltage across this resistor, and this voltage will reach here from this current limit resistor to pin number 4. Pin number 6 have 10K and 47 ohm resistor to drive this MOSFET. At pin number 6 we have R17, a 0 ohm jumper. Then we have this 47 ohm resistor, which is connected to this 103 10K resistor. This junction, it is making a jumper to the gate of this MOSFET. So this MOSFET will take pulses and it will cause to flow the current. This current will generate magnetic field. This magnetic field will transfer voltage in secondary and in auxiliary winding. I draw auxiliary winding here to simplify the circuit. In the output of the auxiliary winding we have two R7 resistor, that is 2.2 ohm resistor. Then we have a diode, and we have C14 capacitor that are connected to pin number 5. These two resistors, initially when this IC is off, these two resistors, 4.4 mega ohm resistor, will take a charging current. So it will charge this capacitor C14. Where is C14? That is here. And a diode. In initial stage, it will charge this capacitor. When this capacitor will charge, the IC will start switching. Here we have 100K resistor, that is to set frequency for this IC. So it will start switching. So the generated magnetic field in the primary will cause to induce voltage in secondary and auxiliary winding. In secondary we will receive voltage. It will pass through this L3. Output of this transformer, secondary side, is connected here between these 2 points, this point and this point. So this line is connected here to this L3, and here we have diodes, rectifier diodes. So it will give output. Then we have these two resistors, a capacitor which is connected parallel to this diode. So it is Snubber circuit for this diode to give a fast recovery. We have a capacitor here, this one. It will charge inductor L1. Here we have L1. After L1 we have another capacitor, the output capacitor. It is 63 volt, 100 microfarad. In some power supplies it is using 120 microfarad, 63 volt, and here it is using 100 microfarad. Then we have dual line filter in the output side, output filter, and two lines, one line and the second line is coming here. In this line we have 523K resistor and 24K resistor in series. It is making a voltage divider. The 57 volt output is connected to two resistors, and these two resistors will divide voltage at 2.495, 2.5 volts. It will apply a reference voltage to this TL431. Where is TL431? TL431 is connected here. When the output is exact 57 volt, then it will give a reference at pin number 1. Here we have ZD1, that is 39 volt Zener, and 850 ohm resistor, series resistor. Then we have PC817 LED. Then we have TL431. Here is a question, why it is using this Zener regulator? Because we have adjustable regulator. Its maximum range is 40 volt. We cannot apply more than 40 volt to anode to cathode, so we have to drop voltage in series. When the voltage will reach here, at that time this Zener regulator, this adjustable Zener regulator will apply cathode current to this PC817 LED. Approximately 39 volt are here, 1 volt drop will here, 39 plus 1, 40 volt, and approximately 16 or 16 plus voltage will apply to this TL431. DC voltage, I have 57 volt here in the output capacitor. It is applying here at this Zener regulator. It is 39 volt. And then we have R10 resistor. It is dropping 394 millivolts. 39 volts dropped here. 400 millivolt, 0.4 volt here. Then we have PC817. This all circuit we can see from this point to ground. From positive terminal Zener, this one, this one, this one. So 4 components, 1, 2, 3, 4 components are series, and all component will drop voltage. So 39 volt at regulator, 0.4 volts at this resistor, current limit resistor, then 1 volt on the optocoupler, and pin number 3 and pin number 2, that's ground. It is dropping 16 volts, 16.5 volt dropped across TL431, 1 volt across optocoupler, plus 0.4 volt across current limit resistor, plus 39 volt, 39 point something volt across this Zener regulator. So 56.9 volt, because we are taking the round figure. Next question, when the supply is started, we applied voltage between ground and this line. It will just only allow to turn on LED when it will receive 57 volt here. For example, if we are receiving 54 volts, 39 here, some voltage are here, less than 1 volt here, and the remaining voltage here, at this point it is very sensitive point, pin number 1. So it must have between ground, pin 2 and pin 1, it must have 2.495 volts to turn on. When it will receive 2.49 volt, or we can say 2.5 volt, we consider as 2.5 volt, basically it is 2.495 volt. When it will receive reference voltage 2.495 volt, in that case it will give a cathode current to this LED. So this LED will conduct, it will give a light. This light will turn on the output transistor of this optocoupler. So optocoupler will connect this ground line. Approximately the voltage drop, that is 1.3 volt, I think 1.3, 1.2. in PC817 condition it is 1.3. sometime it is 1.4 volt, it is 1.35, because 2 junctions are here, NPN junctions. So 1.7, 1.4 volt, around about 1.4 volt will drop across this transistor, and it will connect this ground to this controller. So this controller will know that the output voltage are maintained. So let's check its frequency. Now this IC is working without load. It is maintaining its power saving mode. So it is working at 27, 25, 26 and 4% duty cycle. At minimum duty cycle. Why minimum duty cycle? Because we applied 250 volt. At maximum input with no load, it is working at minimum duty cycle. When we will apply load, this IC will automatically increase its switching frequency. How this circuit will know that load is connected? Normally this capacitor is charged and we have no discharging path here. When we will connect load, so this load will draw a current from this capacitor negative terminal to positive terminal. So when this capacitor will decrease, So our sense line is connected directly to this line. At this point, a millivolt change will drive this reference below the limit. So it will control the cathode current. When it will reduce the cathode current, the light of optocoupler PC817 will decrease. So this decreased light will change the conduction of this transistor and it will increase the internal resistance. So decreased light will cause to increase the resistance of this transistor. So this transistor will give a resistance to pin number 2 and this IC will become to know that there is a voltage drop. So it will increase its duty cycle. We discussed it is working at 4%, maybe it will change to 10%. When it will change 10%, more switching time will allocated to this MOSFET. So more current will flow, more magnetic field, it will cause to more voltage in this winding. So the more voltage will increase and it will compensate the drop in the output section. So this is regulation. If we remove the load, before this the load was connected. Now if we remove the load, in that case the voltage at this capacitor will increase, because when we connect load the voltage source decrease. Now when we remove load, this level will increase. It will cause more current. When it will cause more current, it will increase the light. When the conduction level will change, its internal resistance will decrease. When decrease, this IC will become to know that there is over voltage. To control over voltage, this IC will reduce its switching time, on time vs off time. We have to check the VCC voltage. VCC voltage at this capacitor. DC voltage. So we have this capacitor here. So it's taking 22.8 volt at VCC pin. .8 volt. When we work on SMD, always be careful because these points are very close. Never touch the test lead, test probe between 2 points, so it will damage this IC. So friends, I hope so this video is informative for you. If it is informative, give a thumb up. If you have any question, let me know in the comment box. If you have any suggestion, if you have any question, if you have any idea, let me know in the comment box. If you have not subscribed my channel, subscribe it. And if you want to watch my videos in future, press bell icon button so you will notified on my every new video. Thanks for watching. Assalamu alaikum warahmatullahi wabarakatuh.